Okay, let us go ahead with the exercise 18.3. This problem is to express the Lorentz force by making use of 4-vector P mu and the field strength tensor F mu nu. At the end of the day, we will find F mu nu is a matrix, a 4x4 matrix that looks like this. Okay. In the general physics course, we learned the Lorentz force for a charged particle under electromagnetic field looks like that, except that we do not have 1 over c here. In the MKSA system, we have electric field. The electric force is charged Q times the electric field, and the magnetic force in the magnetic field is Q V cross B. But in the last class, we learned the Heaviside Lorentz unit. Electric field and magnetic field are of the same physical dimension. So multiplying the 1 over c here to make dimensionless quantity. So the electric field and magnetic field have the same dimension. So this is the Lorentz force formula in the Heaviside Lorentz unit. Here, this is a momentum P, and we know that P mu is a 4-vector. So our aim of this today's class is to express this Lorentz force in a covariant form. That means that it transforms following the Lorentz transformation that transforms the for displacement, the for velocity, and for momentum. So for momentum is, as we learned, that the energy divided by speed of light is a zeroth component, and the spatial component is just a normal momentum. And we learned that it is a product of rest mass m0 and the for velocity. And for velocity is gamma c comma gamma v. So for velocity squared is always a c squared in any frame. So in short, the m0 gamma c comma v. So m0 is the rest mass, and gamma is the boost factor, that is 1 over square root 1 minus v squared over c squared. Alright, so we would like to rewrite the left hand side in a spatial component for momentum. Because this is not a covariant form, we have to replace this guy in terms of proper time. dt is gamma d tau, where d tau is the proper time difference. So we replace this force by 1 over gamma times time derivative, the proper time derivative of the 3 momentum. And then we just consider the gamma factor here. This gamma factor in the denominator. Let's see. Okay, this is the electric field. So we factor this speed of light out, and Q over C appears here. And this gamma is multiplied to the right side to make this C, gamma C, and the electric field. And next term is gamma coming from this denominator in the left-hand side, appears here, and velocity here, and speed of light has been factored out, and I copied the magnetic field. So we find that this is gamma C, gamma V. We are familiar with that quantity, that R just came from for velocity. So this is general component of the for velocity, and this is a spatial component of for velocity U. So now we have simplified force, replace the force as derivative with respect to the proper time, then the 3 momentums derivative, time derivative became in this form. We know that this full momentum is the product of rest mass and full velocity. Rest mass and full velocity. And rest mass is independent of the frame, so I can factor the mass m0 out and divide both sides by m0. Then full velocity is a spatial component, have the time derivative with respect to the proper time, q over m0c, and this factor. Next, we remember the full momentum has the zeroth component, which is the energy of the particle divided by the speed of light. So we are interested in the fact that this is a force. If I make a displacement, then F times dx is the increment of the energy of the particle. Work done on the system. Work done by electric and magnetic field on the charged particle. So if I calculate the work, then I find the change in the energy of the particle. So that means P0 can be calculated by making use of the fact that work done on a charged particle increase the energy of the particle. Okay? So let us calculate that work. This is the energy of the particle, time derivative of the energy of the particle with respect to the proper time is, we remember this E over C, so I have 1 over C factor, and F dot dx is the work, and I have the denominator in the proper time, so work F dx and d tau is the denominator. Force is usually calculated, not usually, but exactly, the force is the time derivative of the momentum. It is not the time derivative with respect to the proper time, but real time. And then this is displacement divided by proper time difference, so it is just spatial component of the form momentum. I can replace dt using dt equal gamma d tau. I have factored this gamma out, so gamma c is in the denominator, and the momentum derivative of the momentum with respect to the proper time. And we have already obtained this formula here, and I copy this result in here. Then we have U0 electric field and U cross B here, right? Q over C is factored out, and scalar product with the four velocity, spatial component of four velocity. We know that U cross B is always orthogonal to the U, so we find that the magnetic field does not work at all. And only the electric field does work on the system, and the change in the energy of the particle depends on the electric field only. So if we simplify this, and U0 is gamma C. So if I make use of the gamma C, then gamma C cancels, the over factor is just the Q over C, and electric field scalar product with the full spatial component of the full velocity. So we have found that we have obtained the derivative of the full momentum. This is spatial component, the spatial component, and the zeroth component with respect to the proper time. So let us copy this and this result in here. The full momentum's proper time derivative is dp0 over d tau and the dp over d tau. Let us copy this. Okay, zeroth component here. Q over C E dot U, U dot E, E dot U. And the spatial component here, Q over C, U0, electric field, U plus B. All right. We learned that P mu is a Lorentz 4 vector, and tau is invariant. Therefore, this derivative is still a full vector. Because this is identity, the right-hand side also should be a full vector. And another important thing here is right-hand side is always, there's a single power of u appears everywhere. But this p mu is not proportional to u mu, right? So it is impossible to write dp mu d tau as u mu times the scalar. This is impossible. And there is something, electric field, either electric field or magnetic field. So I'd like to express this expression in this kind of form. This is a four vector and it is linear in u, but index of u does not match exactly with the p mu index. So we can try this kind of solution. There is a tensor f who has two indices and nu has been contracted. So this became a Lorentz scalar. So this whole object behaves like a Lorentz four vector. So I think this is general enough. So let us find the components of f mu. That is called the field strength tensor. All right. The zeroth component, dp0 over d tau, is q over c u dot e. So let me write it as ei ui. If I write in this expression, this is just like f mu 0 u0, f mu 1 u1, f mu 2 u2, f mu 3 u3. So I have to express this one in this way. F, this is zero component. 0, 0, u0, f, 0, I, u, I. But here, ui, this index I is contravariant. I have to put this one down. Then ui in the lower index, that is covariant form, has the difference in the sign as a minus. Therefore, f00 is 0 and f0i is minus electric field. So we have found that f00 is 0, f0i is minus electric field for I equals 1, 2, and 3. Let us compute the spatial part for every index for I. It runs from 1 to 1, 2, and 3. So where is it? This expression. I copied this here. EI, PI, EI, the same component. So EI and U0, this U0 is a contravariant, but for zeroth component, contravariant and covariant, they are the same. The second one is U cross B, and U cross B is I component that is I'm interested in. So Q over C is a vector down, EI, U0, I copied, and I component of U cross B is epsilon ijk, uj, and bk. Again, I have to make use of this kind of expansion. How can I expand like that? uj here, I put this contravariant form, transforming contravariant form into covariant form. Then I have negative sign in front of them. Okay. This is Fi0 U0 and then Fij Uj, something like that. Right? Therefore, the coefficient of U0 is Fi0, that is EI. And coefficient of Uj is minus epsilon ijk bk. Okay? So, what we have found is Q over C F 0 mu U mu and Q over C F I mu U mu. And the summary is like that. 0, 0 is 0. 0I is minus electric field. And I0 is a plus electric field. And Ij is minus epsilon ijk magnetic field. So, we find that 0, 0, 1, 1, 2, 2, 1, 1, 2, 2, 3, 3, all the diagonal components vanish. And if I replace these two indices, I have negative sign. In the case of Ij, if I exchange the two indices Ij, then I have negative sign. So this tensor is completely anti-symmetric. And let us substitute 1, 2, 3. So F01 equals minus E1, F02 minus E2, F03 is minus E3. And here F12 equals 1, 2, 3. Only third component survives. So F12 is minus B3. F23 equals minus B1. F31 is minus B2. In summary, if I substitute these into matrix form, what I find is that mu has the first row 0. This is diagonal components are all vanishing. Minus electric field 1, 2, 3. And F12, 1, 2, that is minus B3. F23, 2, 3, minus B1. F31, minus B2. And then make use of this anti-symmetry. Then this is copied to here, but I have negative sign disappear. And minus B3 is copied to here. I have put minus sign to be plus sign. So B2 here, minus B2 here, minus B1 here, B1 here. So we have found that Lorentz force is expressed as dp mu over d tau equals Q over C F mu mu U mu. Lorentz force is expressed in a very simple form, and it is completely covariant equation. That's it.